Okay, well, I'm going to fire up my DS1102E oscilloscope, and sort of hidden under there is a DG1022 signal generator. Alright, wow. Kind of a mess. So we said we have a gain of 10 and our maximum peak-to-peak voltage would be 5. So half a volt would be as big as we want to go on the input. But let's be generous and say 100 millivolts is what we'll use. I'm going to clip onto here, put this into where my input cap is, and we'll connect up our battery. This is 5 volts. All right. Let's connect channel 1 to the output. Those are just ground down there. And I suppose I'll need another wire. Here, you know what? Sometimes I just take another component like a resistor and stick it in there like that so I can have something to clip on to. I'm not using the resistor really, but alright. Let's set our amplitude to 100 millivolts peak to peak. The frequency is 1 kilohertz sine wave, and then turn it on. We hit the output. Now we'll look at our O-scope. I've turned off channel 2. Look at that. We have little frequency. We have some, I think I have sampling averages. Let's turn that off for now. Yeah. Alright. And if we want to measure what our gain actually is, we'll have to then clip onto the input. You know, you could just take the 100 millivolts, see what the output is, but usually there's some loading that happens, and you know, we might see something just a little less. I guess I can touch it here. Turn on channel 2, and I have it displaying the peak to peak. You see that the input is actually 80 millivolts peak to peak, not 100 like we have it programmed. And the reason for that is the circuit is drawing some current from the input. It has a low input impedance, and that's loading down the signal generator, and it's outputting a little less voltage than it's reading on the screen. So if we want to compensate for that, we can just spin this guy up. Get my screen. Okay, we'll spin this guy up until the oscilloscope says we're at 100. And there we go. And now we see our output volt peak to peak is 860 millivolts. So input 100, output 860. That is a 8.6 gain. And that's, I mean, we calculated 10. 8.6 is decently close to 10, so that's pretty cool. And there's one more thing I want to show. There is a trick to getting higher gain out of this thing, and so we said our equation for gain is RC over RE, but if we throw a bypass cap in here, so way out, we'll put a bypass cap to ground, and that means any AC signal will be able to bypass RE, essentially having zero resistance to ground. So 470 ohms divided by, well, 0 would be a lot. Now, you actually have to take into account the internal base to emitter resistance, like little RE, that will come into play that you normally don't have to deal with when you have a resistor here, like order of magnitude larger. Anyway, we'll still see a much higher gain, so let's check that out. We just need to take it from the emitter to ground. Alright, here's something I could use. These are rather long wires, not ideal for working with amplifiers and small signals. So that's our emitter. We said we want to bypass the emitter resistor, so we'll attach the capacitor above the emitter. Or, yeah. Now, we look back at our oscope and we see, look, it's way off the screen. We're going to have to change that back down. You can see there is a little bit of clipping going on. So that means the swing is so large, it's getting out of the, it's basically bottoming out, you know, at 0 volts. So let's get that brought back in and reasonable, and then we're going to take our peak to peak voltage input down to about, until the oscope reads 50. And now we don't see that clipping going on near as much on the input. Our gain is now from 50 millivolts to about 3 volts. That's a gain of 60. So whereas we had 8.6 putting that capacitor in, now we have 60 times the output voltage, or a voltage gain of 60. Well, I hope you found this exploration as interesting as I did. Thanks for watching.